So chapter 8, which is the final chapter in the course, is all about cryptography. Well, not all about, but is about cryptography, but not all about cryptography, if you know what I mean. So in general, chapter 8 is on cryptography. So the first thing I want to do is I want to go over some terms. So intro. Let's say this chapter is on cryptography. So just some terminology. Just so we know some things that will come up. So first, cryptology. This is the study of encryption. Broadly, encryption, decryption, etc. Second thing is cryptography. Sometimes these terms are used loosely, interchangeably, but they're not really. That's not really true. Cryptography is the study of methods of encryption. So it's a little more specific. The first one is very broad. Well, next one is a cipher. This is a particular method. Of encryption, if you like. Fourth one, cryptanalysis. Or cryptanalysis, sorry, I said that wrong. This is sort of the study of breaking methods. Or analyzing, maybe more succinctly, but analyzing generally with the goal of breaking. Let's say breaking ciphers. And then we've got words that'll come up a lot. Plain text. This is sort of the quote-unquote English language text you want to encrypt. It doesn't have to be words, though it could be a picture or anything like that. This is the thing to encrypt. Encryption, that's sort of backwards. This is the process of applying a cipher to a plain text. So a cipher text, this is the result. This could be scrambled text or a scrambled image or something. And then decryption. This is the process of getting the plain text back. And so in this particular section, 8.1, right? So this just to be clear, this is 8.1 that we're in right now, which is basically on character ciphers, which are some of the most basic methods, but they're good because they get down some of the terminology and they sort of set the stage for what's going on, and we could do some basic cryptanalysis and so on and so forth. So 3, we'll say basic methods. I mean, they're so basic that nobody uses them anymore, but they're still good to get things set. So first of all, we need to talk about character assignment. Everything that we're going to encrypt, at least in this course, is just going to be single words in English. So what we'll do is we'll assign the letters. I'm not going to write out the entire chart here, but we will assign A to be 0, B to be 1, C to be 2, etc. up to Z equals 25. We're just going to use capital letters. We're not going to use spaces, etc. It might annoy you slightly that we're starting at 0 because intuitively we think of A as the first letter of the alphabet, so you think that A should be 1. But it sort of works this way better because we're using modular arithmetic. And so if we work mod 26, the numbers are 0 to 25. So it kind of makes sense to have it this way. So we just sort of have to roll with it. So the first kind is the Caesar cipher. Purportedly, if you like, used by Caesar. As in Julius Caesar. And so the idea is this: we work on the text character by character. So we take each plain text, or let's say each plain text character P. We're going to use an uppercase P for these. Try and make your uppercase P's pretty uppercasey, because in 8.3 we'll have a lowercase p as well, and so you want them to be kind of clear. One thing I can do when I write this, I can like put a serif on it so that it looks different than when I use a lowercase p. So we take each plain text character and we assign C to be, so C will be the ciphertext. This will be the ciphertext character. C is congruent to P plus 3 mod 26. So just to be clear, this is sort of an equation, but we're thinking of it as an assignment. And so really what we're doing here is we take the least non-negative residue of P plus 3 mod 26. And we do this character by character, and then we convert the result back to letters. So let me go through a really, really simple example. So here's an example. So let's encrypt. Say the word Leibniz. So this is with the Caesar cipher. So we first assign the values. So this is using the chart that I didn't do. It's in the notes, but I just didn't necessarily recopy the entire thing. So these are the numbers 11, 4, 8. Don't need commas, but it helps space things out. 1 for B, 13, 8, and 25. Then we take each, we do ciphertext. In other words, take each, let's be really specific, as P, and then we do C is congruent to P plus 3 mod 26. We reduce it. We get the values 14, and not many of them actually spill over and need to be reduced. 7, 11, because I'm really just adding 3 to the numbers that are above. It's only this last one, this 25 plus 8, or plus 3 is 28, which reduces to 2. And then we go back to letters. And we get, in this case, O, H, L, E, Q, L, C. And so, like, overall, this is the original plain text. Actually, let me use a different color just to label this. This is the overall ciphertext. I say overall because you could say that a single character was also a plain text and a single character was a ciphertext, but just to give a context. And so, of course, this final one, this is the thing that gets sent. That hopefully your enemies, when they read it, they won't know what's going on. So this worked for a while, of course, because nobody exactly knew what was going on, right? So to decrypt it, you just subtract 3. And we take the equation, we do P is congruent to C minus 3 mod 26. All right, so pretty straightforward, pretty simple. So what this is a specific example of something called a shift cipher, because it shifts everything along by 1. So C shift cipher. I won't do another example just to give a context. Is the Caesar cipher is just one of these? Let's say is an example. The shift cipher. So where we sort of generically do the ciphertext is the plain text plus B mod 26, where B is some value between 0 and 25. Now, notice you're not going to use 0 because then the plain text and the ciphertext are the same. But in theory, you could, so we'll leave it like this, and this will be relevant when we do the next kind. But 0 would be a stupid choice for a shift cipher. So next one is a sort of a slightly generalized version of this. It's what's called an affine cipher. So these seem like really baby steps, but we'll see this jumps really quickly because we go from shift ciphers to affine ciphers, and then we go to exponentiation ciphers, and they all go along the principle of finding more complicated ways to mess around with the plain text to get the ciphertext. And once we've seen exponentiations, we can move to things like RSA encryption, which is like one of the big ones that's used in the world today. So what we do for an affine cipher is different, right? So what we do here is we don't just pick a B, is we pick an A and a B in the integers. And we do the following. And we have to make some modifications of this, and you'll see why. So we multiply P by A and then add B mod 26. So now B being 0 may be reasonable because the A may mess it up enough, right? And so clearly we can use 26 choices for B again, like meaningful differences. Through 25. But what about the A's? So how about A? In other words, can we use any of those? Or like, yeah, let's say, can we use any A? Well, you wouldn't want to use 0, clearly. That would really mess everything up. But could you, and probably using 1, and then you would just get a shift cipher, but could you use any other A? This is looming question here. So the answer is no. So let's just make sure that we see why. So the answer is no. And the question becomes, why not? So think about decryption, right? So to encrypt, we do this. We do C is congruent to AP plus B mod 26. To decrypt, basically we have to solve for P. This is because we need to be able to get P for any C, right? So we start doing this and we go, all right, C minus B is congruent to AP mod 26. Right? So let me rewrite this. This is a great time to remind ourselves of like what we learned about systems of equation, right? Because this is really a linear congruence. The variable is P. All right, so the question then becomes, what's the case? Like, what's the requirements necessary so that we can solve for P? All right, so this is a linear congruence with variable p. And so just to remember, a linear congruent, this originally, like generally for us, had this form: x is going to be mod c. So you may recall that this guy, this original one, this has a solution, or this has GCD of a comma c solutions, incongruent solutions, but let's just say solutions for now, if and only if the GCD of a and c divides b. So what this means is, for us, in our case, we'd like only one solution, right? It wouldn't make sense if there were more than one p. Right? We'd never decrypt it. So this means we need the GCD of a and 26 to be 1, which means those are the a's we can choose. So using, say, 2 for even numbers are no good. But using, say, 3 is good, but 13 is no good. So again, these are the only a we can choose. If we use an a with GCD of a and 26, not 1, then for each c, we could potentially find more than one p, or we would find more than one p. And that would be no good. So thus, just to be clear, there are, let me spell that right, there are phi of 26, which is 12 choices for each, or for a, and 26 choices for b. Thus, overall, 12 times 26, which is 312 affine ciphers. So, 200 years ago this might have been really good, but nowadays this is no good, because checking 312 different combinations and looking for a result that makes sense is very, very quickly. But just to be clear, let me give you an example of encryption and decryption. I'm not going to worry about giving actual words, because I think it makes sense what we do, but let's say the mapping, say C is congruent to 5p plus 7 mod 26 is an affine cipher. So to decrypt, basically the decryption method we get by solving for p. So we subtract 7. Of course, subtracting 7 is the same as adding 19, but we can of course leave the 7 for right now. So then let me rewrite this in a more friendly way. So now I need to find, basically, because the GCD of 5 and 26 is 1, I know that 5 has a multiplicative inverse. We can find something to multiply by 5 to get 26. So we could be sort of sneaky about this in this case. If we multiply it by negative 5, so negative 5 times 5 is negative 25. So this becomes negative 5c plus 35. And negative 25 is the same as 1. So p is congruent to negative 5 is the same as 21. And 35 is the same as 9 mod 26. So we've got an encryption method. We've got a decryption method. Here is our encryption. Here's our decryption. Otherwise, it works just like a like a shift cipher. Character goes in, character comes out. So again, neither of these is particularly complicated in this day and age, but they're worth investigating. So let me begin by looking at, let me proceed the last thing for this, just while we're looking at a broad overview of things, just to look at look at some things about breaking these ciphers. So first, I'll just mention something really briefly about breaking shift ciphers. Well, two things really. One, which will be sort of what it takes to break a shift cipher, and then a method that comes up, right? So basically, to break a shift cipher, I only need to decrypt one letter, right? So really, like, because what the situation is, we only need B. That's the only thing. That's the only variable in there, right? So if we can find a single P0 corresponding to a single C0, and since C0 is congruent to P0 plus D mod 26, or plus B rather, we find B, and then we can decrypt everything. So one sort of how that comes up, which is like, well, how would you find a specific thing? So one way is just letter frequency, right? So a classic approach is letter frequency. So for example, in English, E is the most common letter of the English language. By far. Okay. So this will be basically our P0. Or basically this would be 4, because that's an E. So then you would look in your ciphertext and look for the most common letter. Let's say the most common ciphertext letter. And this works better if you have a longer string of text, or if it's one word, it's probably not as likely. But if it's a book, for example, it's highly likely. So we'll find the most common ciphertext letter and let that value be C0, and then find B and decrypt. Now, of course, it's entirely possible that somebody who designed the cipher might know that, and they might sort of avoid using the letter E. There's a sort of a somewhat infamous book that has no letter E in the entire book. But so what you do is you decrypt it, and if it makes sense, right? Like if you're decrypting English, if you believe you're decrypting English, then if you do this, then and you get English, then you're pretty much accurate. And if this doesn't work and you get English, then you could like try the next one, right? So we could say if we're sure it's English but makes no sense, then maybe there weren't as many E's as you thought, so maybe P0 would correspond to the next most common letter, which is T. All right, so you try that. And you could keep going. I mean, but you could try everything, right? Like there's only 26 possibilities. So in reality, this is sort of goofy, but it sort of gives you an idea about what's going on. So let's take a look next at breaking affine ciphers. So 5, breaking affine ciphers. So it's not good enough to have just one character, right? So having only, let's say, P0 and C0 isn't good enough. Because, let's say, the equation C0 is congruent to P0, or AP0 rather, plus B mod 26. This isn't enough to solve for A and B. But what if you had two pairs? So, however, we had, let's say, P1 and C1 as well. Right, so then we have the following. Then you have a system of equations. These are mod (26), both of them. So you can solve. We can, let's say, subtract them and factor out. Now, before I make a comment about solving for A here and solving for B and so on, keep in mind the assumption here is that there is an A and a B, right? We're assuming that somebody used an affine cipher, which means there is absolutely a solution A comma B, which means when we look at this, even though it's a linear system, you could argue that there will be a solution if and only if the, because we're solving for A here. So you could argue that there will be a solution if and only if the GCD of P0 minus P1 and 26 is equal to 1. But in this case, like, we're assuming that there's a solution, so we kind of assume that that's the case. Or rather, we assume that the GCD divides C0 minus C1, right? Let me put a little note in here just to clarify what I'm not saying very well. So we're assuming, for right now, affine, which means we assume a solution exists. In other words, we're assuming that the GCD of P0 minus P1 divides C0 minus C1. Now, could there be more than one solution? Let's see, could there be more than one solution? Right, so for example, if the GCD, sorry, I was a little bit sloppy there. This is the GCD of P1, P0 minus P1, comma, 26. It's entirely possible that that GCD is, say, 2, and there could be 2 solutions. So what you would do in each case is you would find the solution, find the B, and try it, right? Now, however, it's usually a bit better than that, so let me sort of explain. So just to clarify, like, we're assuming solution exists, but it could be the case, right? If it were the case that the GCD of P0 minus P1 and 26 were greater than 1, there would be this many, that GCD, possible A. So what we would need to do is, for each A, find B, using, for example, C0 is congruent to A P0 plus B mod 26, and try decrypting. And if you get something sensible, right, let's say if it works, we're done. Otherwise, try try the other A's. So there's a little note here that comes along with this, which is this but, right? So typically if you're doing this with letter frequency, right, so the most common we said is E. And E corresponds to 4. And the second most is T. And T corresponds to 19. So 4 would be our P0 and 19 would be our P1. So in this case, P0 minus P1, make these bars, right, is 4 minus 19. Well, this is really just an equality, which is negative 15. And the GCD, if we look at that, that's P0 minus P1 and 26 is 1. So there would just be one solution. So one possible A. So let me just work through an example so we see how this all pans out. Right? So take a look at the following. So suppose we find the ciphertext. Now I've made this very short, but I've sort of really engineered it to work out nicely. So we're going to do the ciphertext will be WK, K, TBD, KZKK, BPK, CB. So we take a look at that and we do some frequency analysis and we look for the most common and the second most common character. This is what we see in the ciphertext. The most common letter is K. And so K corresponds to the number 10. So we'll call that C0. So what we're going to do is we're going to assume that corresponds to the letter E, right? But before we go that, the second most common, this is again in the ciphertext, is B. B corresponds to 1. And so we'll assume that that's C0 or C1, right? So we make, just to be clear, we make this assumption based upon frequency, right? Or rather, that was sort of said badly. Let me keep going and then we'll clarify. So we assume that C0 equals 10, that matches an E. That'd be the plain text 0, right? Because both of those are the letter E. Like we're assuming this is E. We'll say must be E question mark. That doesn't have to be, right? But probably. Right? And then we assume that C1, which is 1, matches P1, which is 19, because we think that the second one must be T. And of course, this is E, and this is T. So when we say matches, this is what we're assuming, right, to be clear. Right, so we assume that in this case, 10, our C0 is A times 4, our P0 plus B mod 26. And we assume that 1, our C1 is A times 19 plus B mod 26. So again, the first one is corresponding to E. Second one is corresponding to T. If we take this and we solve it, so we subtract. So we get 15a here, the b's cancel. So we solve that. So I'm not going to go through the motions of solving it, the specifics, but a turns out to be, oh hold on, I made a little mistake here. This is a negative 15. Let me put an intermediate step that I have in the notes. This is a negative 15. Negative 15 is the same as 11. So this has solution. Again, I'm not going to show the work of this right now. A is congruent to 15 mod 26. So that's what we know. That's what we know that A is going to be. Right? So then what we do, we take the first equation. So we take 10 is congruent to A 4 right there plus B. And we solve for that, right? So we get B is congruent. This is 10 minus 60. So this is negative 50, which is 2 mod 26. So now we have these two values, A. And really we're saying mod 26, but you know, we're going to assume that they're 2 and 15 because nothing would change if we did something different. So then what we do is we simply go back and we decrypt everything. So just to be really thorough, what we do is I'm going to take all these letters WKK, TBD, K, Z, KKB, PKCB. And I write down the numbers that correspond to these. So 22, 10, 10, 19. Now, just to be clear, let me keep writing these and then I'm going to make a quick comment as we go about what's going on here, because I'm about to write some more numbers and I want to make sure it's clear. So we have 1, 3, 10, 25. We have 10, 10, 1, 15. And then 10, 2, 1. So in this case, the second row that we've got here, this is the ciphertext. So then we need to find the plain text in each case. So what I didn't do yet is I didn't write down the formula for the plain text. So let me do this down here at the bottom and then we'll go back up. So our assumption here, or like what we believe is the case really, or what we think is the case given the A and the B, is that the ciphertext, we know A is 15 times the plain text plus 2 mod 26. So to decrypt, right, what we do is we subtract the 2. Let me write it this way around. So the multiplicative inverse of 15 is 7. In other words, 7 times 15 is 1. So what we're doing in each case is we're taking the ciphertext, and this could be rewritten in nicer ways. Like you could multiply the 7 out, you can write 7c minus 14, you can write 7c plus 12, however you want to. We're taking this and we're using this to calculate the p's above. So this gives us the values 10, 4, 4. Those 4 4s should be familiar. 15, 19, 7, 4, 5, 4, 4. 19, 13, 4, 0, 19. And again, just to clarify, because I think I didn't clarify that very well, this transition is done using this equation. Then we take each of the p's and we write down the English letter that corresponds. So we have K, E, E, P, T, H. Now keep in mind as we go that that in a sort of a quote-unquote real-world situation, as you're doing this, you're looking to see that you get English, and if you are, then you assume that your decryption, that your breaking of the code is correct. So then we go feet, F-E-E-T-N-E-E-T. So looks like it says keep the feet neat. Again, there are no spaces. We didn't necessarily need the spaces, but we get English, so it looks like we did the right thing. And hold on, I made a spelling mistake. That is not, that is a badly spelled word, neat. And so we decrypted. So again, this was a very basic introduction, but it lays down some of the essentials, right? We have a plain text we need to encrypt. We have a ciphertext that results. We have a method of encryption. We have possibilities of breaking it. We have some experimentation. We get to see that, different levels of encryption will be harder. Just a shift is really easy, but an affine cipher is a little trickier. We need more information to break it, and so on. So what we're going to do next is we're going to look at what happens when we go from an affine cipher to an exponentiation cipher, changing the way that we encrypt it, changing the modular statement that we do, and then what's required and how that all works. So we'll do that in 8.3.